For decades, the rule of stellar death has been simple. When a star between 10 and 25 times the mass of our Sun runs out of fuel, its core collapses, triggering a blindingly bright supernova that can outshine an entire galaxy. But astronomers using the Large Binocular Telescope in Arizona decided to test that rule. They launched a survey about nothing, monitoring 1 million massive stars across nearby galaxies to see if any would do the unthinkable, disappear without making a sound. In 2014, they found a primary suspect. A massive star in the Andromeda Galaxy, known as M31 2014 DS1, began to show signs that the traditional rules of physics were about to be broken. Most astronomical surveys are designed to find the appearance of new light. This project flipped the scientific method on its head, operating on the belief that the sudden absence of a star could be the most significant discovery of all. The timeline of M31 2014 DS1 began with a curious surge in infrared brightness in 2014, but 2 years later, that light began to plummet, fading far faster than any normal stellar cycle would allow. By 2023, the star had vanished from the visible spectrum entirely. Deep imaging confirmed the location was empty, yet there was no record of the brilliant supernova flash that usually accompanies the death of a star this large. This total disappearance presents a physical paradox. A supergiant of this mass cannot simply expire without a trace, yet we have no record of an explosion. It suggests the star's internal mechanics failed in a way that challenges our current understanding of how the most massive objects in the universe end their lives. To understand how a star can vanish, we have to look at the first stage of core collapse. When the nuclear furnace at the center of the star shuts off, gravity instantly crushes the core into a dense sphere, a neutron star. In a successful supernova, this collapse releases a massive flood of neutrinos. This energy creates an outward shockwave so powerful that it overcomes the star's gravity and blows the outer layers into space. But in some massive stars, that outward shockwave is too weak. Instead of blowing the star apart, it's overwhelmed by the massive weight of inward falling gas. The core continues to cave in, bypassing the neutron star phase entirely, collapsing directly into a black hole. This internal failure is the reason we see nothing. The explosion is essentially smothered at its source, prevented from ever reaching the surface and releasing its light into the universe. But this raises a mechanical question. If the core is a black hole, why doesn't the rest of the star instantly fall down the drain? The answer is convection. Churning gases in the star's outer layers create powerful angular momentum. When the black hole forms, this orbiting gas spirals inward slowly. The outermost layers are pushed away, cooling into a thick, opaque dust shell that blocks the remaining light. We can see the evidence of this process in the infrared spectrum. When astronomers pointed mid-infrared telescopes at the star's former coordinates, they detected a faint, lingering heat, the thermal signature of that silicate dust shell. The star isn't actually missing. It is still there, hidden inside a dusty cocoon of its own making, slowly feeding a new black hole in the dark. This discovery solves a long-standing statistical anomaly known as the missing supernova problem. Astronomers have long noticed a discrepancy. We observe far fewer supernova explosions than the birth rate of massive stars suggests we should. There has always been a mathematical void where these explosions should be. The failed supernova model fills that void perfectly. It accounts for the stars that are reaching the end of their lives and dying quietly, without the bright display we've been trained to expect. What we once interpreted as a lack of data was actually the evidence of a different, silent evolutionary path for the universe's largest stars. We can now verify this silent death using gravitational wave observatories like LIGO, which detect the collisions of black holes instead of searching for light. These detectors revealed an anomaly called the mass gap. Standard supernovae are so violent that they blow away most of a star's mass, leaving only small black holes behind. Yet LIGO keeps detecting black holes that are unexpectedly heavy. Direct collapse explains why these heavy black holes exist. Because there is no explosion to blow the star apart, the black hole can swallow and retain the massive weight of the star's helium core. up to 30% of massive stars may die in total silence. It proves that some of the most violent and transformative events in the cosmos can happen right in front of us, completely under the radar.